residual current of 0.4 milliamps is kind of a figure that we've just decided upon. There's not really any sort of scientific rationale behind it. Okay, so I'm going to start heating. For this bond, temperature is 370 degrees. So if we have a quick look now through there, we can see through these viewports, the heaters are both on. The heating performance is very good, it will heat up very quickly.
So this illumination from the heaters?
Yes.
What's in there?
So you can see the light source is from the heater bulbs. So they're filament bulbs, 6 of them. 6 of them in a ring in series, powering the heating the upper platen, and another 6 heating the lower platen. So they're independently heated.
So there's no physical contact to the wafer?
Not yet.
I mean, the heater doesn't physically contact the wafer?
No.
Just
No, it's yes, exactly. Yeah. So what we're seeing here now, we're seeing the pressure start to rise. So this is from outgassing now that we've started heating up the platens. We want to keep an eye on that. Ideally, we don't want the pressure to rise above 5 times 10 to the minus 3 millibar. If that happens, we have to turn the heater off, wait for the pump to pump out the outgassing products, and then turn the heater back on again. But it seems to be holding steady at the moment, so that's not too bad. Usually by the time it reaches 200 degrees, the outgassing is sort of mostly over. No, not really.
It needs to be
Yeah, if you could do better if you only need a gap of like a couple of millimeters at the bottom there to allow the airflow to come out.
It's a little too much. It's like everything's coming from outside, I think.
Yeah. So the idea is you want that, if you had that Velcro to the floor, that would still allow enough flow to come out. What you ideally want is a positive pressure in here to keep the outside out. I don't think these fans are going to be strong enough to be able to maintain a positive pressure with that level of gap at the bottom. So yeah, you're right there, that could be improved. Ideally what you have is solid walls all the way around, and then you have an extractor. So you have air being blown in through the filter and extracted through, and other things. You have a laminar flow. That's the kind of optimal, that's how a clean room would work.
So if we are not bonding prime wafers, let's say edged wafers, we want to do like seal cap or whatever, something like that. So we have cavities.
Yeah.
So we want to lower the current, right?
No, it would probably be okay. So, I mean, yeah, you would still use 4 milliamps, but you'd probably expect to see less charge transfer because it's proportionate to the surface area, the bonded surface area. So if you have cavities, obviously there's no bond developing there. So you'd expect to see a bit less charge transfer, and the bond would also take less time to form.
when we use the hot plate and these 2 electrodes, get up to 20 milliamps.
Yeah.
20 milliamps. And we don't have any control or anything.
Yeah.
Just like we heat it up with the voltage.
Yeah. Now this power supply is quite sophisticated that we can control it, and we can control both the voltage and the current. Whichever is predominating at whichever time during the bond, it will automatically use that to control itself.
Are you thinking about using it for bubbles?
Bubbles, not for the cavities.
So I'm saying last to cavity instead of plate, or you talking about direct bond?
Even for the sealing.
Silicon to glass? Why not Anodic?
Need to be lower temperature. In fact, for the to reflow the glass inside. Or making bubbles. You can work at high pressure. Then you don't need vacuum.
Yeah, but potentially you could basically use the same thing instead of hot plate, right?
This, yeah. I mean,
You just like
for making bubbles, we don't want to use the vacuum furnace. You can like bonding at high pressure.
this one saying you could actually use a high pressure, so and
I'm not sure whether you'll be able to do anodic bonding at high pressure on this tool. That might not work. It might break down. It might just create plasma and have a breakdown. I'm not sure. You can try, but it may not work. Generally, we would always do anodic bonding under vacuum. Okay.
Can we do it in atmospheric pressure?
Maybe. I've never tried. I can't say yes or no. My gut feeling would be no, but I don't know that for a fact. Okay, so our wafers are up to temperature now. So I'm going to apply a clamping force of 500 newtons. The exact force isn't really important. It doesn't matter. It's just a matter of bringing the wafers into contact and holding them there, holding them together.
So we already have a 0 point here.
Yes, yeah, I've already set that up. I'll show you how to do that later on, or potentially tomorrow, depending on how we get on with time. Yeah, I need to show you things like platen leveling and how to change heater bulbs, and if you take one platen out, you need to re-level it and reset the 0 position and all this kind of thing. So that's all kind of part of the machine configuration training, if you like, which we'll probably save for tomorrow. We'll do the bonding now. Okay, so we've got our force being applied now. It's nice and steady. So now is the moment of truth, whether the bond is going to work. Say a little prayer to the bonding fairies. Good, it's working.
why is it turning red? It's just in progress?
So the red line is plotting the current, and the white line is the voltage.
No, the button itself, the on button.
The on button, yeah, that's just warning you that that it's on.
Okay.
So there we are. The current's ramped up, nice and controlled, topped out at 4 milliamps. Now we're going to start noticing. So at the moment, to maintain 4 milliamps, we only need 50 odd volts. It's hardly anything. As the bond develops, as more and more charge is transferred, that voltage is going to need to get higher and higher. So you can start seeing it to ramp up now. It's going to ramp up until it reaches 800 volts. The danger moment is always when you turn this on. If you've got the screw heights wrong or you've got the wafer clamp nose height set wrong, it'll short at that point and then you can try again, but same thing always happens. So you have to go back and adjust your setup and start over. So it's good, it's working.
What kind of glass are you using?
Borafloat. I think it's not necessarily critical what kind of glass it is, but it is critical that there's doping, some sodium or potassium, and some oxide ions in there to migrate around and actually create the bond. So I think what's happening is the sodium ions are migrating up towards the platen, and they plate out on the back, either on the back side of the bond, or in our case, it seems to plate out onto the platen itself, which keeps the bond nice and clean at least. And then oxide ions are migrating towards the silicon wafer, and that will make siloxane bonds, chemical bonds across the interface. I'm just going to grab a quick drink of water while we wait for that to carry on. Excuse me a second.
Flashing to maintain the temperature.
Yes, yeah, exactly, yeah, it's pulsing. So there are some little PID controllers which are behind this panel on the bottom right. All we do is send a signal to them, set the temperature, and then they control the heaters. So we're approaching the crossover point now. I like to set the scaling on these axes so that the crossover point is just flat at the top. It's not important, it's just kind of Helps us gauge when it's about to finish or when it's about to transition. Right, so now we are voltage limited. Holding voltage at 800 volts and the current's going to start to decay exponentially. There it goes, yeah, good. We've got good charge transfer here. I'd expect to see 1500 to 2000 millicoulomb charge transfer for a 4-inch wafer. So already at 1600, so it's going well. Can be reasonably confident this bond has worked. If we were to inspect this bond under a scanning microscope or something like that, we'd probably find there'd be some particle voids in it, but they're not particularly large with an anodic bond. So a speck of dust on the wafer will create a void, say 0.5 millimeter to 1 millimeter wide, whereas with a direct bond, one particle can ruin the bond. So you can end up having one particle create a void of 1.5 centimeters kind of thing all the way across. So for anodic bonding, cleanliness isn't so critical. For direct bonding, it really is critical. So I think we're approaching the end of the bond now, so we can see there's not really much happening with the charge transfer anymore. It's pretty much topped out. The residual current hasn't quite decayed away to our arbitrary 0.4 milliamps, but I think basically the bond is done now. I'll let it.
It's better to keep the machine under vacuum.
When you're not using it, you mean?
Yeah.
Yeah, that's probably good practice to do that. One thing to be aware of, when you leave the machine under vacuum, you'll come back the next morning and you're going to notice that the Z height has changed, which is because there's a difference in the leak rate between the chamber and the force compensators. So the force compensators, which are pulling the Z drive down, leak more quickly than the chamber. So essentially they're going to become vented, and then what will happen is that the manipulator will gradually move up. So just be aware that that's going to have happened when you come back the next morning. It doesn't.
Like a few days, is it safe?
Yeah, it's perfectly fine. Yeah. It's just to save you some head scratching. Think why I didn't move the manipulator and it's moved itself up. That's why that happens. Yeah, I'd say leaving it under vacuum is good practice. Keeps it clean and sealed inside the chamber. It's a good idea. So to leave it under vacuum, what you do is pump it down, close the isolation valve, and then switch everything off. Nearly there. Yeah, so with your hot plate bonder, did you say what did you see you observe current wise 20 milliamp or something, was it? Yeah, so essentially what's happening in your machine is that's going up to 20 and then decaying down to here, whereas all we've done is just kind of controlled that bit. So you'd still see the same voltage ramp while this was ramping up, while the bond's forming, and then you'd see the same exponential decay but just over a larger range. Doing this current limitation, it helps to prevent heat stressing and just generally cracking the wafers and things like that, so it can it's just a more controlled, cleaner kind of process. There we go, that's 0.4 milliamps, job done. So to exit the bond now, turn off the bonding voltage. That's going to gradually decay down to nothing. There we go. Next thing, important, but I often forget to do it, is to turn off the heaters. So I've often stopped pumping, opened the nitrogen cooling, and it goes down to about 320 degrees and won't cool anymore. And I'm thinking, why won't it cool down? Why won't it cool down? Because I've left the heater on. It's easy to do. Someone will probably leave the heater on at some point and start venting. It won't do any damage, but it'll just waste your nitrogen. So, while it's under vacuum, I'm going to separate the wafers. So what I want now is, I'm going to do now is release that clamp and separate. So what I'm hoping will happen now is that the bonded pair will drop onto the lower platen and move away. Sometimes there's kind of stiction between the wafer and the upper platen, so you can release the clamp, but it just stays there. So you open the lid again, you've got the bonded pair on the upper platen. That,
Not